Welcome back, everyone. Let's jump straight into today's explainer. We are tackling a true classic when it comes to coding problems, finding the lowest common ancestor, or LCA, in a binary tree. Look, if you've ever felt totally tangled up in tree traversals, or if recursion makes your head spin a bit, you are in the exact right place. We're going to use pure visual intuition today to completely demystify this problem and help you build a rock-solid mental model of how the solution actually works.
Okay, here's our quick roadmap for today. We'll start by defining the LCA problem, move into visualizing the ancestry rules, outline the lowest ancestor conditions, implement our depth-first search algorithm, and wrap up with algorithm complexity.
All right, Section 1, defining the LCA problem.
At its core, you can really just think of this as a massive family tree. The lowest common ancestor is simply the lowest node in a binary tree that has both of our target nodes, which we'll call P and Q, as its descendants. But, there's a really crucial caveat you got to keep in mind here. A node can actually be considered an ancestor of itself. Keep that little detail in your back pocket because it is a vital piece of the puzzle when we start writing our logic later on.
To see what this actually means in practice, imagine our target node P is the 8, way down there at the bottom left, and target Q is the 7, over on the right. If we trace their lineage upward, node 3 is the lowest connection point for both of them. Sure, the root node, node 1, is also an ancestor to both targets, but node 3 is the lowest one down in the tree structure.
Now, before we try to build any kind of logic, we really need to know our boundaries. The constraints for this problem? Actually, they're super friendly. The tree will always contain at least 2 nodes, so thankfully, we don't have to stress about weird empty tree edge cases. All the node values are completely unique, saving us from duplicate value headaches. And target nodes P and Q, they represent completely different, distinct nodes in the tree. So, nice, clean rules.
Section 2, visualizing ancestry rules. I want you to pause and just visualize the tree for a second. To actually find the lowest common ancestor, where do our target nodes P and Q absolutely have to live relative to that ancestor? Like, what are the literal spatial boundaries we're working with here? Let's zoom right in on node 3 to figure this out. If we're traversing through our tree and we land on this specific node, how do we systematically prove if it's an ancestor to P and Q? Well, we have to look downward. And this right here is the absolute crux of it. Both P and Q absolutely must be located somewhere within node 3's highlighted subtree. If they are both anywhere inside that specific zone, node 3 is their ancestor. But if either P or Q is sitting completely outside of this subtree, let's say hanging out over in the left branch under node 2, then node 3 is not an ancestor to both. It really is a strict spatial boundary.
Section 3, the lowest ancestor conditions. Okay, so when determining the lowest ancestor, location is quite literally everything. Notice the contrast here. When our targets P and Q are split perfectly between the left and right sides, or if one of the targets actually is the current node, then boom, that node is the lowest common ancestor. But what if both targets, say 8 and 9, are buried deep inside just the left subtree? Well, then the current node is an ancestor, sure, but it is not the lowest one. A node further down, like node 6 in this case, contains both of them, making node 6 the true LCA.
This brings us to a really beautiful, consistent pattern. For literally any given node we're evaluating, our targets P and Q can only exist in 3 specific buckets. Number 1, the current node itself might actually be P or Q. Number 2, the target could be hiding down in the current node's left subtree. Or number 3, the target could be located in the current node's right subtree. And that brings us to the core logic, the absolute game changer for this problem, the 2 out of 3 rule. A node is the lowest common ancestor if, and literally only if, exactly 2 of those 3 locations we just mapped out contain our target nodes. Think about it. If P is in the left subtree and Q is in the right subtree, that's 2 locations. If the current node itself is P and Q is in the left subtree, that's 2 locations. It's just incredibly elegant logic.
Section 4, depth-first search algorithm.
Now we're going to bring in depth-first search, but really just as a vehicle to check our rule. At every single node we hit, we just want to grab 3 simple Boolean variables, true or false flags. First, is the current node equal to P or Q? Second, does a DFS of the left subtree find a match? And third, does a DFS of the right subtree find a match?
So how do those DFS calls actually know if there's a match buried deeper down? It's all in the recursive return. Whenever we make a recursive call on a subtree, we tell the function, hey, return true if any of those 3 variables trigger a match. If P or Q is anywhere in that subtree, we send a massive true signal back up the chain.
It's so cool to watch this in motion. As the algorithm runs, these true and false values just bubble up from the bottom of the tree. Node 8 returns a true up to node 6, node 7 returns a true up to node 3, now node 3 looks at its own variables. The left subtree shouted true, and the right subtree shouted true. That is exactly 2 out of 3. This completely identifies node 3 as the exact spot where 2 true signals converge, confidently locking it in as our lowest common ancestor.
Section 5. Algorithm complexity. When we start talking about scale, this approach is actually highly efficient. Both our time and space complexities operate in linear time, which we represent as big O of n. To break that down just a little bit further, n simply represents the total number of nodes in our binary tree. The time complexity is O of n because, in the absolute worst-case scenario, our algorithm has to traverse and check every single node exactly once. And our space complexity, also O of n. Why? Because the memory used by our recursive call stack scales dynamically with the maximum height of the tree. In the worst case, say you have a totally unbalanced tree that looks more like a straight line, that height equals n.
All right, we have successfully mapped out the core logic for the lowest common ancestor. But before we go, I want to leave you with a slightly provocative thought to chew on. How might this exact depth-first search logic change if the tree wasn't strictly binary, but instead had dozens of branches per node? Or, to make it even more practical, how does this very type of tree traversal impact the indexing of the massive real-world databases you rely on every single day? It's honestly fascinating to think about how these foundational algorithmic rules scale up into the massive systems that literally run our digital world. Keep exploring, keep learning, and I'll catch you in the next explainer.